Hello everyone, let me know if you can hear me, and then I will start today's lecture. Just write something in chat. Okay, soon, thank you. Great, so today we're going to discuss about kernel methods. So this is a generic approach for machine learning, and there are different particular classifiers that are part of this category of methods, and we will discuss about one of the easiest ones to understand, which is ridge regression. So this is based on classic linear regression with L2 regularization. And we will continue the discussion about kernel methods also in the next lecture. Yeah, and we will also make a smooth pass to neural networks, but first let's go back to kernel methods. So kernel methods appeared after neural networks, so we will discuss actually them in reverse order, but this is not that important. We are making this choice because actually neural networks are I think are a bit more complex than kernel methods, and we're trying to present them in increasing order of complexity. Okay, so first we had in about the year 50s, Frank Rosenblatt introduced the perceptron, and this is a linear model which is useful also to gain some insight about linear models in general, and also this is the main component in multi-layer neural networks, which were introduced in the 80s. And later in the 90s, people started using kernel methods because they are easier to optimize and provide more stable results. And yeah, more recently people started using more complex approaches. Okay, so the perceptron is a linear model that looks something like this. It tries to model a neuron. So it's a mathematical model of the of neurons in our brain. So it has some input, vector x, some weights assigned to the input vectors. And we also have this bias term, which is modeled with a different weight, and these are summed up together. And we also have the sign transfer function, which gives us the output. So for classification purposes, we have the input examples denoted by x. We have some weights assigned to each feature that characterizes an input example, and then we have an output for the respective example that can be 1 or -1. So this is a binary label for the corresponding input. Okay, so this is the model of the perceptron. I think I'll discuss more about the link with biology when we discuss about neural networks. So right now I'll try to give you the spatial or geometrical interpretation of this model. So actually here the equation. So here we use bold letters to denote vectors. So W is the vector formed of W0, W1 to Wn, and X is the vector X1, X2, Xn. So if you look at this equation in the space r to the power n, then the equation gives us a hyperplane. So this is the equation of a hyperplane. So in a particular case, let's say in a three-dimensional space, this will be the equation will be the equation of a plane, and in a two-dimensional space will be the equation of a line. So here I'm giving you the example of this this particular case in the two-dimensional space. So two-dimensional, it means that the input vectors x have two dimensions, x1 and x2. Okay, and for each of these components, we have some weights that are assigned. So we have a weight W1 that is assigned to x1, and the weight W2 that is assigned to x2. So these, if you write down this equation, so this will be x1. So also here in this slide, I'm using another term for this this W0, which is B. So actually this term is called bias. So this is why it's noted usually with B. But if you think of the equation for the 2D case, you will figure out that, I don't know, W1 times x1 plus W2 times x2 plus B is similar to the equation of a straight line that passes through the point x1 and x2. So the points that have components x1 and x2, and the parameters of the line are W1, W2, and B. So in the geometrical interpretation of these parameters, so we have W1 and W2. So if we put together these components, they will give us a vector W, which is this vector is normal with respect to the line, the line that is defined by these parameters. And the bias gives us the distance from the origin of this model. So actually W controls the orientation of this line, and B controls the position with respect to the origin. Okay, so essentially we can model any line in a 2D space. If we go to the three-dimensional space, the equivalent will be a plane. So we can we'll have a three-dimensional vector W that is the norm vector with respect to this plane, and the plane can have any orientation. Then we also have a bias with respect to the origin and so on. Okay, so the main idea, the equation of this line is equal to 0. So this means that any point that is on the line will be when we replace the components of the respective point in this equation, it will give us the value 0. If we have points that are on the same side as the norm vector, so we note that the same line can be denoted by a vector that has the norm like this, but also the vector can have the norm in exactly the opposite direction. But actually there is a difference. It's not the same line, it's a different line, because in this case, when we have let's say a point in this region, we will obtain a positive value. So if the point is in the same side with the with this norm vector, then we will have a positive value, and then if it's on the other side, we will have a negative value. So then when we apply the sine function on top of this output, we will have the labels +1 for this pink region, and the labels -1 for this white region. Okay, so this is the linear model, typical linear model, and the goal is to usually we apply this type of model to binary classification problems. So we have let's say some points that have label +1 and some points that have label -1. And the problem is to find the line that separates these points such that we obtain a good accuracy. So most of the points with class +1 are on this side, and most of the points with class -1 are on this other side. Okay, so yeah, this is a linear model, and usually all the kernel methods are also linear model. This doesn't mean that the perceptron is a kernel method. It's just a linear model, but there are also other linear models that have slightly different equations. So for example, instead of the sine function, that have I don't know, can have a different type of output. And also the way we optimize these weights is different. So for the perceptron, there is a very simple algorithm that actually works only if the points can be separated by a line. But in many cases, there can be some intersections between the two classes. So we cannot draw a line such that all points will have 100% accuracy. So in this case, you will not be able to train the perceptron until convergence. But for Kellner methods, there are ways to optimize this line and still have good results, even if there are some intersections. Anyway, so this is a geometrical interpretation of linear models, which is also important for kernel methods. So yeah, so remember that this perceptron was proposed in the 50s, and then in the 60s there was a report by Minsky and Papert to scientists in AI that argued against the perceptron, saying that is a simple model that cannot model non-linearly separable problems. And they gave the example with the XOR problem, the logical XOR problem, where you want to, for example, solve to draw a line that that classifies the points according to the labels. So imagine these 4 squares here are points. So we have 2 axes that are oriented like this. So from top to right and left to right and top to bottom. And you have this point here, this point. And the labels are 0, 1, and 1 and 0. So the labels correspond, so are given based on the XOR problem. Okay, so here we also have an example for yeah, I'm not sure if this is actually 1 and 0, 0. Yeah, so it's maybe, yeah, not very representative, but anyway. So for example, if you have the OR problem, the logical OR or the logical AND problem, you will be able to classify the respective points with a line. But if you have this configuration with the XOR problem, no matter how you try to draw the line here, you will not be able to separate the points labeled with 1 on one side and those with 0 on the other side. Okay, so this is a non-linear classification problem, and it cannot be solved with a simple linear model in a straightforward way. So this problem was addressed with 2 solutions. I think the first one historically is to use neural networks. So okay, a single perceptron cannot solve the problem, but if we organize them into some structured neural network with so these are different different perceptrons that are organized in some layers, and we have the input vectors here and some output here. By using these neural architectures, this type of neural architectures, we can obtain here actually non-linear decision boundaries. So a neural network that has hidden, at least one hidden layer, can model any data points that are non-linearly separable. So for example, a neural network can learn this separating boundary very easily. Okay, so one approach is to use this model and to combine them into more complex model in order to achieve non-linear decision boundaries, and the other solution is to use kernel methods. So this is the topic for today, and kernel methods are commonly based on two steps. First, they embed the data in a higher dimensional Hilbert space, and then they search for linear relations in this embedding space. So imagine, for example, for the XOR problem, we have two-dimensional space. So imagine we take these points and we embed them in a higher dimensional space where those points can now be separated linearly. So I will show you a drawing in the next slide, and you can figure it out more easily. Okay, so the embedding can be performed implicitly by specifying the scalar product among the data samples. So instead of providing an embedding function, this can also be done by computing the scalar product among every pair of data samples. So we will discuss in more detail today about these aspects of kernel methods, and we will also see some concrete examples on how to use them. Okay, so this observation, when we do the embedding implicitly, then it means that we can actually do the second step directly without providing the embedding, and this is done by representing the data in the dual form. So we will discuss next about this dual form representation, and how we can go from the primal form representation to the dual form for rich regression, and also we will discuss more details about different ways to compute the scalar product, or actually the scalar product can be replaced with similarity between pairs of data samples. So there are different similarity functions that can be used here, and they can provide different performance levels. Okay, so about the embedding, so imagine that you have this two-dimensional space, and then you embed the data from this space in a three-dimensional space where the relations become linear, or I don't know, even a higher dimensional space where non-linear relations from this original space become linear in the embedding space. So usually this is achieved by increasing the number of components from the original space to the embedding space, but this is not the only way to do it. It can the embedding can also be, for example, the identity function, and kernel methods can also work in this direction. Okay, so as I said before, so if you do this in the dual representation, then you do not need to represent the points. You just you can skip this part and actually use a different representation that is given by the scalar product between pairs of points. Okay, so actually this is also called the kernel trick. So it's a term that is commonly used in scientific articles and books explaining kernel methods. So the kernel trick is to replace the scalar product with a pairwise similarity function, such that you don't need to perform the embedding, but you just need to compute the similarity directly. Okay, and this is one example with the scalar product. And here, actually, what I didn't said before is that the embedding that corresponds to the scalar product is the identity function. So we're discussing the most simple case here first, and then we will once we figure out how to do the dual representation for kernel ridge regression, then we will also discuss about replacing the scalar product with other similarity functions. Okay, so yeah, going on. So there is the primal form of the linear classification problem. So we will introduce these notations, and we will also use them for the dual form. So we have some training samples denoted by X. So here, just not to be confused with the example for the perceptron. So here an input vector is x1, another input vector is x2, and so on. So the individual values, so the features of these input data samples are denoted by f1, f2, and f7. So we have 4 data samples, and we have each data sample is represented by 7 features. And all these are put together in a matrix X. So we will, for kernel methods, we will prefer to use matrix notations. So we're going to introduce the notation right here from the primal form. And we assume that we have some labels for these data samples. So let's assume a binary classification problem with labels, with labels 1 and -1. And what we want to do with this data is to learn some classifier C. So the classifier is a linear classifier defined by a vector of weights. So we have here, if we have 7 features, we will have 7 weights and the bias term. Okay, and the linear classifier will give the output L by multiplying the vector X, the matrix X with this vector of weights W and adding the bias term. Okay, so this is a classification problem. So we want to determine the vector of weights W such that we obtain, when we apply this equation, we obtain the labels L. Okay, so this is the learning part. Then we go to the evaluation part, or the inference part, where we want to apply the model. So when we apply the model, we have some test samples denoted by Y. So we have 3 test samples. So the test samples have the same number of features as the training samples, and these are denoted by the matrix Y, and they have some unknown labels that we want to predict. So in order to predict these labels, we apply the classifier C. So applying the classifier means that we do sign of this equation in order to get P. Okay, so this is a machine learning, a linear machine learning problem in primal form. And in the dual form, what we said before with kernel methods is that we do not use the embedding or the characteristics of the data samples, but we use instead the scalar products between pairs of data points. So here this is illustrated like this. So as I said, we prefer to use matrix notations. So For example, in order to compute the scalar product, this can be computed by multiplying the matrix X with its transpose, and we obtain the matrix denoted by K of X. So we use here K because this is a kernel matrix. So we will come back to this matrix soon. So okay, so we have this new representation of the data, which is a square matrix. So it has the same number of columns as the number of rows. So here we have 4 rows and 4 columns, and we have the pairwise similarities between every pair of training data samples. So here we have the similarity, for example, between x1 and x2. And of course, this matrix for the training examples is symmetric with respect to the main diagonal. Okay, so if we look at these examples, for example, let's try to compute the scalar product between the vectors x1 and x2. So we just multiply the components and sum up the results. So here we have 0 plus 0 plus 2 plus 15 plus 12 and plus 2. So we have 2 plus 15, 17 plus 12, 29 plus 2, 31. So yeah, the scalar product between x1 and x2 is 31, and of course the scalar product between x2 and x1 is also 31. Okay, so yeah, this is the kernel matrix. So now we can also train the classifier using this information. So here actually the classifier will learn some weights which we commonly denote with alpha, and we also have the bias term, which is the same as in the primal form. Such that we apply this linear model on the kernel matrix and we obtain the labels L. So the main idea here is to remember that these problem formulations are completely equivalent, and we will see that there is actually a direct direct relation between the weights W and the weights alpha. So actually the weights W are equal to X transpose multiplied with the weights alpha. So there is a direct relation. If you have the matrix of data samples and these weights, you can compute the weights W directly. And when you do the optimization, you can use either the primal form or the dual form for a kernel method. The main idea is that when you use this dual representation, in some cases it can be more efficient. So right now it's not directly obvious, because we started from this matrix X and then we use the scalar product to compute the kernel matrix, and this takes more computation, and we also have to represent the data like this. But actually what you can do in practice is you can compute directly this kernel matrix without building the entire matrix X. So it can be more efficient if, for example, we have more features than data samples. Okay, so let's stay here on the dual form formulation, just to explain how we apply the model at test time. So this is a very important thing to remember, because people here confuse a bit how the kernel matrix for test time is computed. So yeah, if you think about the learning problem and see it like this, it may seem easy. Yeah, the weights that we learn here are associated to the examples. So here the classifier associates some example to some weight to a data example based on how important the data sample is for the learning process, and it can have a positive weight or a negative weight. Okay, so good. So you learn this set of weights, of 4 weights, and then at test time, what do you do? The first idea that comes to mind um, is to compute the pairwise similarity between test samples. So you just compute y times y transpose. So this is wrong because actually, if you think about what happens during training, as I explained before, you learn some weights for the training data sample. So actually, in order to apply the model, you need to compute the similarity between each test sample and each training sample. So here, instead of computing y times y transpose, you will have to compute y times x transpose. So this is the correct way to do it. Okay, so y times x transpose. So this means that at test time, your kernel matrix will not it will not be a square matrix, so will not have the same number of rows as the number of columns, because here we have the number of test data samples. So here, for example, I don't know, if we apply this model, I don't know, for spam detection. So of course, for training, you have a number of emails that you want to train your model on, and for test time, you will have a different number of emails that you want to apply your model on. So you compute the similarity between each test sample and each training sample. So this, once again, you can do this using matrix multiplication, but using here the correct components. And once you have computed the similarities, you can apply the model. So the model is just multiplying the kernel matrix with the weights, with the dual weights alpha, and obtaining the predictions. Okay, so these two formulations are perfectly equivalent, and next we will also see how we can demonstrate this for linear regression with regularization. Okay, so in linear regression, so we start with a regression problem, but just bear in mind that kernel ridge regression can also be used for classification successfully, and it can outperform models for that are specifically designed for classification. So even if you hear the name of the method is kernel ridge regression, so it's typically designed for regression problems, it can also be applied successfully for classification. You just, so yeah, because this is this is just a linear model in the end. So if you want to use it as a regression problem, you just want, okay, I want to find the vector of weights W and the bias term that gives me, so in the case of classification, then gives me positive scores for the examples from this class and negative scores for the example from this class. So this is what you do during the optimization. You disregard the sign function, and then when you actually apply the model, you just apply the sign. So essentially, for kernel ridge regression, you do the optimization for this part of the equation, for k of x times the dual weights plus the bias. You ignore the sign. So anyway, going back to the standard linear regression, the goal is to obtain a function g that has some weights multiplied with your inputs x and gives you the output g. And for these data samples x, y, you have some labels denoted by y. So once again, here we change the notation from before. So these are data samples. So in bold, we have vectors. So we have the vector x1, x2, xl, and we have the associated targets y1, y2, yl. Okay, here we have the components of the vector. So we have a vector x, and we have the components xy. So here you note that x is not bolded, so this is a component in the vector x, and you compute the output for a vector x by multiplying the weights wi with the components xy. So the vector n has n components, so denoted, you also note that we have here vectors from erla n, and the number of vectors is L. Okay, so just to make sure that we understand the notations here. So these are the notations that we use. Okay, so this is the graphical interpretation of linear regression. So we have some data points on the axis x, and we have some labels for these data points. So the labels can be any real value, so they are represented on this axis y. And the goal in linear regression is to learn a hyperplane that interpolates these data points with minimum loss, and the loss is actually measured as the sum of these errors that gives us the distance. So on the y-axis is the distance from the correct label y to the value predicted by this model. So the value will always be on the line, the predicted value, and of course if the line passes exactly to the data point, then you have the exact output. Otherwise you get the output that is close by. So in regression you do not typically expect to reproduce the exact value, but to have the smallest possible error. Okay, so this is the linear regression problem. So we have this error for some data sample x with respect to its corresponding output y. So considering all training data points, we have this sum of squared losses, so sum of squared errors. So the loss for the linear regression is typically denoted by this function L, round L. So it's the sum of the differences between the correct predictions and the ground truth output and the predictions of the model. And this can also be rewritten as epsilon sum of all these epsilon components square. So I think this should be epsilon I here. I forgot an I. And yeah, this is it can also be written like this. So different ways to write it. The main idea is that is the sum of these squared errors. So actually we will prefer to use the vectorial notation. So the error epsilon is y minus x times w. So this is the function g computed. So it's a vector of values with respect to all the input data samples. So the matrix X contains all the data samples. When we multiply X with the weight vector, we obtain the corresponding outputs for all the data points in our training data. And then we just subtract these values from X. So here we do the difference between two vectors. Y is bold, so this is a vector. And here we also obtain a vector and just compute these differences. So epsilon here is also bold, so epsilon is a vector. So then the loss can also be written as the norm of this vector epsilon, and it can also be written like this. So it's this vector, so this is the vector epsilon transpose times the vector non-transposed. Okay, so this is the loss function that we optimize. So what it means is that we want to find the w. So the parameters that we want to learn are w. That give us the smallest possible error. So the smallest possible error means that the loss function or the norm of this vector has to be minimum. And one question for you is, I would like you to answer, what is the optimal value for W in this case? So for this loss function, I'm giving you an extra hint, is that the loss is a convex function. So we know that it has one global optimum that can be obtained. So what do you think? How do you think we can find this optimum point? Okay, so let's see an answer. Okay, so you already answered, so it means that the delay is not that big. So yeah, I think we have a good answer. So the gradient must be 0 because the function is constant in the minimum point. That's the right answer. So yeah, considering the gradient of this loss function, so we know that for some point on the loss function, the gradient shows us the direction of the steepest ascent. So in the negative direction of the gradient, we can find the minimum, but in the location of the minimum here, the function is constant. So actually, the interpretation would be that if the function is increasing, then the gradient is positive. If the function is decreasing with respect to the direction of the axis. So for example, if we go on the axis W1 and we start here and we go in this direction, the function here is decreasing, so the gradient is negative. Then when the function is constant, so the tangent is parallel with this plane, we have the minimum point here, and the function is constant, so the gradient will be 0, and then the function starts to increase once again, and here it will be positive because the function is increasing. So indeed, the optimal solution is to use the gradient. So we know that the gradient of the loss function should be 0. So then we just have to compute the gradient of this function with respect to W, and then we can compute W from this equation. So the gradient, starting from this notation here, we can multiply here and have y squared minus 2 times y multiplied with x and w, and we also have x w squared. So when we do the derivate, the gradient with respect to w, then we have, so the derivative of this function with respect to w will be, so we have two components that have w and one component that contains only y. So when we do the derivation with respect to w, this part will be 0, so it will get eliminated, and we have one component with w, so w disappears from it, and we have minus 2 x transpose y, and we have a component with w squared, so then the square comes here in front, and we have 2 times x transpose x or w. So this is the gradient computed. So denote, remember that these are also are always matrices or vectors here, and this is equal to the 0 vector. Okay. Okay, so yeah, from this we get the normal equation. So we just move this component to the other side of the equal sign, and we divide by 2 in both in both left and right terms, and we have this normal equation, and from this equation we can compute W as the so we multiply with the inverse of this matrix to the left side, and then we have the solution for W. So of course the solution can be computed if the inverse of this matrix exists. Otherwise the solution might not exist. So in order to solve this ill-posed problem, the scientists proposed ridge regression, which adds a regularization term to the problem. So this actually translates to adding some positive values to the main diagonal of this matrix, and this makes the matrix more inversible. So actually we know that the unit matrix is reversible, and actually this property is somewhat continuous. So if we have a matrix that has dominant values on the main diagonal, it is likely that it will be more inversible. So essentially the idea is just to add these positive components on the main diagonal of this matrix, and in order to do this, actually, if you go back to the loss function, this means that you add the norm of the vector W to the minimization problem. And here you can control the magnitude of the components that you add on the main diagonal with the parameter lambda. So the parameter, this parameter controls the magnitude on the main diagonal. But it also has a different interpretation in the minimization problem. So here in the minimization problem, it controls the importance of the vector of the norm of the weight vector with respect to the objective that we want to achieve. So of course, yeah, this is kind of related, right? So if you want to make sure, for example, that you can compute a solution and your matrix is reversible, then if you use a very big lambda, you can find a solution, but actually you will give a very big importance to minimizing this weight vector and not to the objective that you have. So if you add very big values, you can find a solution, but your solution will not be very useful. So this is equivalent to underfitting the model. Then, so the main idea is to use a small lambda that is just enough to give you a good solution that generalizes well. So this is also related to model generalization. Okay, so now we have this updated loss function, and we try. So it is a convex problem. So once again, the solution is given in the point where the gradient is equal to 0. So now we have to compute the gradient with respect to this loss function. So here we have two components. We have this component, and the gradient is computed the same as before, and we also have the gradient with respect to this other component. So here, if we think about the components in W, in the norm we have the square root, the square of each component in W, and when we compute the gradient, this translates to 2 times W. So each component is squared, so it means that we take the square and we put it in front, and yeah, lambda stays there in place. So we have this value of the gradient with respect to w, and from this equation we try to extract w. So we keep all terms with w on the left side and move all the other terms without w on the right side. Here we use the w as common factor in these two terms, and then we have this matrix that we can move to the other side by multiplying to the left side with its inverse. So then we obtain the solution w is equal to this part. Okay, so yeah, here, as I explained before, it is just equivalent to adding some positive constant values on the diagonal of this matrix. So when we do the sum of this matrix and the sum of the identity matrix with respect to and multiplied with lambda, we just add some small components to the diagonal of this matrix to make it invertible. Okay, so far we discussed about standard ridge regression. So how do we solve for the dual problem? So in dual ridge regression, we have we start from the primal normal equation, that is the equation here, and here we try to we do a trick here in order to compute the solution. So we have we try to extract w from one of the terms, one of these two terms. So here w is equal with this term minus this term multiplied with lambda, the inverse of lambda. Okay, so w is computed like this. We also observe that these two terms have x transpose in common on the left side, so we can actually take out x transpose from these two terms and write the equation like this. And here at this point, we also recall that the relation between w and the dual weights is equal to x transpose alpha. So we use this equation here, and then we take these terms down here to extract alpha from it. So yeah, this is just a rewriting of these two left and right terms here, and then alpha is equal to this equation. So we have x transpose in both cases here. Lambda is a scalar, so it can be moved anywhere. So this is just it can be added here. So then we have x transpose multiplied to the left. So we can multiply both terms with the inverse, so we can eliminate x transpose, and we are left with this equation. So alpha is equal to the weights alpha are equal to the inverse of lambda times y minus x multiplied with w. So what we want here is to obtain the dual solution for ridge regression. So we want to have to express alpha only based on y and x. So we still have w. But just what we said before, that w is equal with x transpose alpha. So what we can do here is just to once again we replace w with this equation. So we have this equation that contains alpha and no w. So what remains to do from this point is to make sure that alpha is only on one side of this this equation. So we rewrite this equation on the next slide. So now we try to put all terms with alpha on the same side. So we multiply lambda on the other side. So we can remove the parentheses here, and we can transfer this term with a positive plus sign on the other side. So now we have lambda on the left side, and all terms with lambda on the left side, and the remaining term without lambda on the other side. Here we have sorry, not lambda, alpha. So yeah, the dual weights alpha. So here we have the dual weights alpha multiplied, multiplying both terms to the right. So we can extract it as a common factor. So we have this equation here, and then we multiply this equation with the inverse of this matrix to the left, and we obtain this this solution. And actually here in the same time we also use the notation, so this is called the Gram matrix, or if it corresponds to the scalar product, it is known as the Gram matrix. If it corresponds to different or any kernel function, it is known as a kernel matrix. So the kernel matrix, recall from the previous slide with the dual form, is equal to x times x transpose. So this is just a notation that we're using. So G is equal to x or x transpose. So this is the inverse of this matrix here. And yeah, we see that the regularization term here has the same effect on this matrix. So this is a diagonal symmetric symmetric matrix, and we add these components on the diagonal to make it invertible in order to obtain solution for the regression problem. Okay, so this is the equation for the dual weights alpha, and once again, so we can solve this equation. We obtain the weights alpha. If we want to obtain the weights w, we can apply this this formula. We can also optimize the problem with respect to the primal problem, which is this one. But here, yeah, we have to do a bit more computation. So you see that the equation for the dual problem is a bit more easier to compute. Okay, so yeah, this is dual ridge regression and how we can obtain the solution for alpha from the primal form. So as I said before, we use the notation G to denote x times x transpose, and this is called the Gram matrix. So each component in this Gram matrix contains the scalar product between some vector x or some data sample xi and some data sample xj. Okay, so yeah. So as I said before, we can actually obtain the solution for dual ridge regression by using the inner product between pairs of training data points. So we do not need to represent them in the primal form. So this information is contained in the matrix G. And the predictive function, so once we have the weights alpha, recall that in the primal form we have to multiply w with x. So this is a scalar product between w and x. And in the dual form here we have to, from the equation, so from the relation w equals x transpose alpha, if we look at the individual components, this means that in order to obtain the weight, or actually, yeah, so the weight w for x, we can multiply alpha I with xi, but here we can also rewrite this as the sum of the weights alpha I multiplied with a scalar product between the vectors xi and the vector x. Okay, so yeah, this is the how we get the prediction. Yeah, this is just to recall the previous notation. So the prediction is computed here. So these scalar products here, the sum of these scalar products means the sum of these components, and these are multiplied with the weights alpha I. So yeah, we can compute the scalar product and multiply with the weights. So this is also equivalent to multiplying the data samples xi with the weights and then computing the scalar products. Okay, so yeah, moving on, let me just see if there are any questions. Not so far. All good. So yeah, now as I said before, we can actually replace the scalar product with any kernel function, and this is called the kernel trick. So first, before we can find out what kernel functions we can use here. So the scalar product is actually a similarity function between pairs of data points. So similarity function means that a higher value, it means that the two examples are more similar, and a smaller value means that the two examples are different from each other. Okay, so it's actually the reverse as for a distance function. So for the distance function, we have a small value if the points are close together, and the high value if the points are farther away. For a similarity function, the reverse is valid. So the higher the value, the more similar the points. So this is just an intuitive idea of what a similarity function is, but we also have a definition. So actually, I think the slide is coming a bit later. So yeah, just trying to figure out. Okay, so yeah, in practice, you can replace the scalar product with a similarity function, and then you will use the notation K, which is the kernel matrix that corresponds to the similarity function. And then the predictive function, when you have a kernel matrix, you replace the scalar product between training samples and the test sample with the kernel function between x, y, and x. Okay, so this is the solution for kernel ridge regression. So then we have the Python implementation. So we have kernel ridge regression in Python is equivalent to this to this solution. So we just compute the dual weights alpha as the product between the kernel matrix K and the training examples denoted here by T train. And here we also have the regularization term, which has the regularization parameter lambda, and multiplied with the identity matrix with n components. And first we compute the inverse of this matrix. So this equation here is actually, yeah, the equation from this slide, or this slide here. So we have the kernel matrix plus the lambda, or the identity matrix, the inverse, and we multiply it with the labels, the vector of labels y. Okay, so once again, we have, assuming that we have the data as a matrix X, we can compute the kernel matrix as x times x transpose. And then we can compute the dual weights alpha. So this is the training part. We can see how the model performs on the training. So we can apply the model on the training data to get some answers regarding the performance on the training data. So in order to get the prediction, we multiply the learned weights alpha with the kernel k, and then we just apply the sign function afterwards. So in order to get the labels, we apply the sign function, and then we can obtain an accuracy on the training data. And then for the test samples, we can do the same thing. So here, just recall that we have the test samples in a matrix X and the corresponding test labels, so we can use these in order to evaluate the model. First, we need to compute the kernel matrix for the test data, which is multiplying the test data samples with the training data samples X. So we also have to transpose them here. Then we have the kernel matrix. We just multiply this kernel matrix with the learned weights alpha, and then we have the predictions for a binary classification problem, let's say, by computing the sign over these predicted scores. And then we have the accuracy on the test data by comparing the predicted labels with actually the ground truth labels. Okay, so the main point here was that you can actually implement this machine learning algorithm known as kernel ridge regression in Python from scratch. You don't need any machine learning libraries in order to implement it. It's pretty straightforward. So okay, so just going on with the definition of kernel functions. So there is a kernel function k that is defined on the scalar Cartesian product of the space of input data samples X, and it outputs a real value. So it has the codomain R. So yeah, the definition. So we say that the function is a kernel function if it has an associated embedding function denoted by phi. So phi is denoted is a function that takes an input data sample X and embeds it in a Hilbert space F, such that for any points X, Z, we have the solution as follows. So K, the kernel matrix, the kernel function, the value of the kernel function between two data samples X and Z is equal to the scalar product between the embeddings of X and Z. Okay, so we also have the definition. So if we have a similarity function that follows this definition, then we have a kernel function that we can use as a way to compute the similarity in a kernel method. And another way, so there are many functions that we cannot say which is the embedding mapping, and I will also give you some examples of kernel functions for which the embedding is infinite. So it's defined on here M is infinite, sorry, for not M, the embedding. So the result here is defined on the Hilbert space has an infinite number of components. And because it has an infinite number of components, you cannot compute phi of X and do the scalar product. So one way to prove that a function is kernel, you can either define the embedding map, the embedding function phi, or the alternative solution is to prove that the corresponding kernel matrix is symmetric and finitely positive semi-definite. Okay, so okay, I'm going to give you some examples of kernel functions. I have I need to take a break of 1 minute. So I'm just going to end the stream temporarily and come back in 1 minute. Okay, so I'm back streaming. I want to make sure that you can hear me before I continue with the slides. So if someone can write something down in the chat so that I can know. Okay, perfectly. So I'm going on. Sorry for the interruption. Okay, so we explained the definition. So now we're going to see some examples of kernel functions, alternative kernel functions that we can use instead of the simple scalar product. So just going back to the original problem of the XOR function. So actually, if we want to embed the data into higher dimensional space, we will not use the scalar product or the linear kernel, which are equivalent. So remember that the scalar product and the linear kernel are the same thing. So they have, either way you call it, it has the embedding function phi equal to the identity. So this means it doesn't do any embedding. It just allows you to apply the kernel classifier in the dual form. But if you really want to embed the data into higher dimensional space, you will have to use different kernel functions. Of course, this is useful in many cases, but there are also situations in which it is not useful. If you think also of the curse of dimensionality that I discussed 2 weeks ago, if you increase the embedding space by too much, you will probably you will not always obtain better results. So it also depends on the complexity of the problem that you aim to solve. So if it's a really complex problem, you can also try to embed the data into a higher dimensional space. Okay, but the main idea is just not to do this blindly. So okay, let's now focus on the example. So here we have a first example of an embedding function. So here we have this kernel that we have the embedding defined as follows. So it embeds the data from a planar space to a three-dimensional space. And the embedding is defined as follows. So the components for the three-dimensional space are defined as x1 squared, square root of 2 multiplied with x1, x2, and x2 squared. So if we have these points in the original space, here we have a nonlinear separation problem. So if we have these x points, blue x's from one class and the red dots from the other class, the only way to separate them is through an ellipse. So we cannot separate them with a straight line. So then if we use this embedding will project the points in this three-dimensional space like this. And here in the three-dimensional space, we can have a plane that separates the point. So this is a linear separation, linearly separating hyperplane that divides the point in the two classes correctly. Okay, so we had the previous the kernel from the previous slide. It is actually equivalent also to to this notation. It's actually the squared of the scalar product to the power of 2. So yeah, trying to define to explicitly compute the components. So we have we consider this definition of the kernel function. So we compute the embedding, then the scalar product, and now we compute the scalar product. So we multiply the corresponding components and we add them up. So we have this this result. So here we have the Newton binomial, and it is equal to x1 z1 x2 z2 all to the power of 2, and this is actually the scalar product between the vectors x and z. So we obtain this equation. Okay, and an interesting note is that we obtain the same kernel if we use an embedding from a two-dimensional space to a four-dimensional space with these components. So if we consider these components, when we do the multiplications, we will obtain here the same result. So we will have twice these, and we will get the same result. Okay, so these are this is a particular case of what is known as the polynomial kernel. So the more generic formulation is the scalar product between the vectors plus positive constant c, and all is raised to the power d. So d is a natural number. So for example, polynomial kernel is a generalization of the linear kernel. So if we use c equals 0 and d equal 1, we have the linear kernel, or the standard scalar product. If we use c equals 0 and d equal 2, we obtain the previous kernel, so from the previous example. And in general, we have this generic notation. So we note that the constant c controls the amount or the influence of the individual polynomials of various degrees, and the power d controls the degree of the polynomials. As you use higher degree, you will obtain a more complex embedding. So you will embed the data points in a higher dimensional space, and thus you will have higher chances of finding linear relations between the data points and finding a linear separating border. Okay, another example of kernel function is the Gaussian kernel, also known as the radial basis function kernel. So in this kernel we have we do not have an associated embedding. It is defined as the exponential function, or the Euler number raised to the power of minus the norm, the square norm of the difference between x and z, divided by 2 times sigma squared. So this is an interesting kernel. It has an application when we have, for example, the Euclidean distance between data points. We can see here from the second. So when we explicit here the notation, we can see here that this is equivalent to the Euclidean distance between x and z. So this means that using this kernel, we can use the Euclidean distance as a kernel. So we can compute, for example, the distance between pairs of points, and then we apply this transformation component-wise. So we raise the distance to the power. So you have e minus to the power minus the distance divided by 2 times sigma, and we obtain a kernel function that we can use with kernel methods. So this kernel also applies to other distance functions. So it can be used here. We can actually replace the Euclidean distance with other distance functions and still obtain a kernel function. And actually, this formulation also works even if the distance here is not a distance function. So even if it doesn't respect, for example, the triangle inequality, you can use it you can integrate it into a RBF kernel and optimize a kernel classifier and obtain still good performance in practice. So yeah, and in that case, the kernel is not or it is, at least it is hard to prove that it is still a kernel function. So in theory it is not a kernel function, but in practice it still works and can provide good results. Okay, I wanted to say one more thing here, but I don't recall. Oh yeah, about sigma. So sigma is a parameter that controls the magnitude of the similarity with respect to the distance. So here, for example, if of course the distance can go to infinity. So when you apply this function, the distance will be when we have distance 0, this will have e to the power of 0, so it will be equal to 1. And here, if you have a very large distance, this will asymptotically approach the value of 0. So sigma controls how soon these values go down to 0. Okay, so yeah, actually I think I forgot to update my slides here because I had some way to visualize the exponential function, but yeah. Okay, moving forward to the intersection kernel. So this is another way to compute a similarity between pairs of data samples. So here we illustrate the example for the values x and z as before. So these are vectors from four-dimensional space. So the intersection kernel is computed as the minimum between the corresponding components and summing up these values. So it is the minimum between 1 and 5 plus the minimum between 2 and 1 and so on. So this also gives us a similarity function. It is demonstrated that this is a kernel function, and it can be used with successful results in many problems, many classification problems. Okay, and we also have other kernel functions such as the Hellinger kernel. So this kernel is defined as the square root of the scalar product between x and z. And we also, in a recent, or maybe not so recent work, but more recent than the other kernels that I presented above, we also introduced in a paper another kernel function that seems to produce better results, at least when the examples x and z are histograms of, I don't know, that represent frequencies of words or frequencies of visual words and so on. So for this kernel, we actually transformed the Kendall-Tau the Kendall-Tau measure that I presented, I think in the second lecture. We transformed that into a kernel function. So the kernel is defined as 2 times the difference between p minus q. So notice here that we do not have the normalization as in Kendall tau. And we also had the demonstration that this function is actually a kernel function according to the definition. So yeah, essentially, how do you compute it? So if you have two two histograms, you compute it as the number of concordant pairs among the two histograms minus the number of discordant pairs, which is q. So you take all pairs from these two components and you compute the value. And actually, the interesting thing, you can compute this kernel in a more efficient way than just taking all the possible pairs, which will lead to a quadratic complexity. You can compute it in n log n complexity using merge sort. So you just try to sort the components from one histogram with respect to its values, and you sort in the same time the components from the other histogram. And when you have them sorted, you just measure, you do a linear pass to compute the final value for the kernel. So that was also a contribution in this paper, and we also have an open source implementation of this kernel function. So far I presented generic kernel functions that can be used essentially for any data types. And I'm going to also present a specific example of kernel functions that are used for text and for sentences, and in general for, I don't know, documents, so in natural language processing. But also on, I don't know, any sequences of characters. So for example, they have also been used on DNA to find proteins and so on. Okay, so essentially string kernels are a measure of similarity between strings, and they are essentially based on counting the number of what we call n-grams, or continuous subsequences of characters that two strings have in common. So the two strings are the strings that we compute the similarity. Okay, so the main idea here is that we have a very simple solution. We for natural language processing, we do not have to tokenize the text and to extract words. We simply interpret the documents as a sequence of characters, so just as two strings. And this also gives us language independence. So it means that the approach can be applied on any language without caring about how the writing is and so on. You just have a digital representation of the characters of the written text in the language and use that representation. So you don't need to, I don't know, to find the punctuation, to do any hardcore pre-processing. Okay, so yeah, one example here, we have some strings s and t. So here these are just two simple words to give you an idea about how to compute the similarity between these two strings. But in general, we can actually consider that s and t are entire documents or sentences or whatever we want to classify. So these are defined over an alphabet of letters. So we have some letters from, let's say, I don't know, the English alphabet or the Romanian alphabet. It depends on what text documents we want to classify. And we establish length for the continuous subsequence, and we, as I said before, these subsequences are called n-grams. So n-grams means sequences of 2 characters in this case, if p is equal to 2. So we have this parameter p, we have the hash maps s and t, and these hash maps are computed from the original strings, and they will contain key value pairs such that the key is an n-gram from, for example, for s, for the string s, we have the hash map s, and it will have 2 grams from the string s, and for each 2 gram we have the number of occurrences. So we build this dictionary of key values pairs for each of the 2 strings. So the dictionary can look something like this. So I'm not sure if I had, yeah, so we have one example here where the n-gram, the b-gram pi appears twice. So here the number of occurrences is 2. Okay, so we build these hash maps, and then, for example, in order to compute the number of common n-grams in the 2 substrings, we just, for example, take or enumerate the n-grams in one of the hash maps, and we look them out in the other hash map. So the idea with hash maps is that we can compute this similarity, the string kernel similarity between S and T, without having to represent our text documents in the primal form through some vectors of occurrences of n-grams. So we can do it more efficiently by building these hash maps and by doing a lookup in the hash map in complexity, in constant time. Okay, so now for string kernels, there are different ways to compute string kernels that are equivalent. For example, we have the presence bit string kernel, which actually assumes that we do not use the actual number of occurrences. We just replace. We actually use only one occurrence. So here we will have 1 instead of 2, and we also have the histogram intersection string kernel, which is based on the minimum, so we can adapt this, where was it, the intersection string kernel. This kernel can also be adapted to string kernel, so we can compute the minimum. So for example, if we have here the n-grams pi that appears twice and here appears once, we add the minimum of these 2, or we can also use the scalar product, so we compute the product between the number of occurrences of pi in S and pi in T and so on. So anyway, so this assumes actually that we use only the values 0 and 1. So 1 means that the n-gram appears in the string, and 0 means that it is missing. So actually in the hash table, we only have the n-grams that appear only once. And in order to compute the similarity, we just, as I said before, we enumerate the n-grams from one hash table, we look them up in the other, and we add 1 to the kernel similarity, and in this case we have 7 n-grams in common, so the value of the similarity will be 7. So yeah, these are quite similar given that the number of letters is not that high. So anyway, this is the way you compute this similarity between 2 data samples. So this is actually how you compute one cell in the kernel matrix. So you have to do this for the entire kernel matrix to obtain the corresponding kernel matrix for these string kernels. Okay, and now in the end, I'm going to show you some applications of these kernel methods where they achieve very good performance. So they obtain state-of-the-art results in problems such as native language identification and dialect identification. So these are results that we obtain in recent works. And yeah, I'm going to explain a few more details about native language identification, where this kind of approach works very well. So the idea in native language identification is that we have some text documents written, let's say, in English, and we have some labels associated to the text documents. And the labels are actually corresponding to the native language of the people who wrote the respective documents. So let's say that all documents in the dataset are written in English, but they are written by French people, by Romanian, by Spanish, and so on. So we have these labels that tell us the native language of the writer that produced the English document, and we have to classify the documents according to their country of origin. So this means that we can actually identify the origin of a person, the country of origin, based on the English writing. So this means that there are some specific patterns. There could be, I don't know, mistakes or preference of some word choice that is a bias that comes from the native language. So it seems that we can identify these patterns quite accurately using string kernels and kernel methods, more specifically kernel ridge regression. Okay, so one example. So in general, kernel methods are useful when the number of features is much higher than the number of samples, and is impractical to represent the data in the primal form. So going back to our example, native language identification. So in the paper referred here, we applied it on the corpus provided by TOEFL, and the number of unique n-grams in this corpus is around 4 million and a half. So essentially, and the number of documents in the training data is 11,000. So if you want to represent the data in the primal form, so just to represent, I don't know, each document as a histogram with the frequencies of the n-grams that appear in the respective document, well, the document will be represented by a vector with 4 million components, 4 million and a half. And the matrix X in the primal form will have 11,000 components by 4 million. So it will be a very large matrix that we have to make room for in our memory. But if we use the dual notation, it means that we have to compute a kernel matrix for the training data that has 11,000 by 11,000 components. So the kernel matrix will be much smaller than using the matrix X. So in this case, the kernel methods will be more efficient in terms of space and and they will allow us to use less computational resources in order to train an effective model. Okay, and another interesting thing is that the string kernels also generalize better than, for example, methods that work with words. So, of course, if you want to use a method and to avoid to compute the space with n-grams, and if you want to use a method in the primal form or a different classifier, you can use, for example, the representation given by the bag of words. So you just consider all the words that appear in the corpus, and this will be much smaller than the number of n-grams. However, the n-grams can generalize better than words. What I mean here is that, for example, a certain pattern, like this pattern for French, with the double n here, which is specific to French, and seems that they tend to make this mistake in English and to write words with double n. This can actually appear in different contexts. So just to look at these examples, so this n-gram, this 5-letter n-gram, can appear in different words like additionally and personal, and it can generalize to different contexts and different words, but it's kind of the same mistake. While if you use words, assuming that you have, I don't know, personal in the training, and if you encounter the word additionally written with this mistake, you will not be able to identify it. So using words will not generalize as well as using these n-grams that are just part of words that can appear, I don't know, in words. So here we also have this the duplication of letter P that can appear in the word develop or developer or underdeveloped and so on. And of course, yeah, the method also identified patterns like, for example, people in France. So there are also these patterns that are mistakes made by people in France, but the method also finds patterns that, for example, people in France talk about France and people in Turkey talk about Turkey and so on. So you can also see in this table the most discriminative patterns. The example for German, we have the word German, or for French we have the word franc, which is short for France, or so on. Yeah, okay, another example. So they can also, so the n-grams can also cover entire words. So here we have the word example, which is written as in French with an E instead of an A. So yeah, n-grams can also be words. Okay, and yeah, we're approaching, I think, the end. Let me see if there are questions. So far, so good. No questions. Okay, so okay, we discussed about kernel functions, different ways to compute the similarities between examples. But you can also try to obtain new kernel functions from existing kernel functions. So this can also be studied on respective to the application. So for example, you can obtain a new kernel function by summing up to kernel functions, or by multiplying a kernel function with a scalar, or by computing the product between two kernel functions, or by applying some function on top of the input data samples X and Z, and then doing the product between the values returned by this function. And you can also use a symmetric semi-definite matrix that kind of gives you the similarity between X and Z and so on. So this is different ways to compute the similarity. And another important aspect with data is data normalization. So we're going to discuss some more in detail in the or other aspects about data normalization in future lectures. But here an important thing to consider. So going back to this example with string kernels. So one problem here is, so looking at the similarity function. So imagine here that one of the strings is very large. So the string, for example, has a lot of sentences and thus a lot of n-grams. So then usually when I compute the similarity between T and S, just because S is larger, it will have a higher probability of finding the n-grams from T in S. So it will artificially increase the similarity between S and T. So essentially the length of the documents will influence also the similarity. So if we have a longer document, it will have a usually higher similarity with the other data samples. And here we can solve this situation by dividing the similarity, the resulted similarity with according to the length of the two strings. So this can be performed here in the primal form. If we do the embedding, then we just compute the norm of the embedded vector, and we divide each component with respect to the norm. And we can also do this in the dual form. So if we do not go through the embedding and compute the kernel matrix directly, we can compute directly the normalized values by dividing the similarity between xi and xj with respect to the square root of the similarity between xi with itself and the similarity between xj with itself. So these two similarities are actually proportional to the length of the vectors. So imagine here that for xi we have the same hash maps in the two cases. So when we enumerate one hash map and look up in the other, we will find all the n-grams, so the similarity will be very high. Okay, so if the similarity has so if x has a few n-grams, then we will have a very high similarity. If x has only a few if it has a few n-grams, it will have a small similarity. If it has a lot of n-grams, it will have a higher similarity. So it will scale the similarity between xi and xj with respect to its length. So this is the equation for doing this component-wise. And we also have the equation to compute the normalized kernel matrix using using matrix multiplication. So here we take the values from the main diagonal, we multiply them, and then we divide component-wise with the values from the resulted matrix here. So this is a column vector, this is a row vector. When we multiply them, we obtain a square matrix. We extract the square root from this matrix component-wise, and then we divide each component in the matrix K with each component here. So in Python, we can do data normalization, as I said before, in the primal form. So we can do it using the linear algebra package. So we have the norm of the vector, we can compute it and then divide x with the norms. So this is done on the entire dataset X. Of course, you can also use the scikit-learn library using the norm scaler and so on. And this is how you do it in the dual form. So once you compute the kernel matrix, you take take out the main diagonal, which contains these components. The main diagonal is the similarities of each example with itself. So we have the main diagonal, and yeah, we have to add a new component to make it a column, so that when we transpose it, it becomes a column vector. So this is a simple vector. We add a new axis, it becomes a row vector, and then we transform it here by transposing into a column vector multiplied with a row vector, and then we do here the division component wise. Okay, and yeah, regarding the normalization, I think in the examples, so let me just go back. So in the meantime, until I go back to the slide that I want, you can ask questions. Yeah, I wanted to go back to this slide. So if you look at these vectors, so for example, x1 has a higher norm, so it has components with usually it has components with larger values, and for example x4 has components with smaller values. Okay, so when you compute the similarities, if you look on the rows with x4, because it has a smaller norms, usually these similarities are smaller. If you look on the rows with x1, the similarities are usually higher. Okay, so this can affect the classifier, and it is important to normalize the data before you train the classifier in order to obtain good results. Okay, because the norm of the vectors can influence the similarities. You need to divide the similarities by the components on the main diagonal. So example, and after you do this division, you will see that the values in the kernel matrix will be between 0 and 1. So this means that, for example, on the main diagonal, you will always have the maximum similarity between the vector with itself. So the main diagonal will be filled with 1, and in the rest you will have values between 1 and 0. So that are proportional to the similarity between the examples, but not proportional to their length. So yeah, data normalization is very, very important here. Okay, it took some time. Okay, yeah, I will post it. I'm very busy until 16 November, so I will not be able to post the competition till then. I will try to do it in the weekend after. So I already have in mind what the competition will be about. I just need some time to prepare the data and to post it online. So anyway, so you will have enough time to play in the competition. Will probably be by the end of the year. We will also see if we maybe extend it to January or not. I will decide later on this. I just want to make sure that you have at least 1 full month to participate. So no worries about that. Okay, any questions related to the lecture for today? Okay, so it seems that that there aren't any questions. So guys, thank you for participating. I'm sorry for keeping you so late. Hopefully next time we'll be able to finish in time. Okay, thank you once again.